1.2, we need to discuss what we mean by initial value problem. So when we have an initial value problem, we're talking about um, a differential equation, and one notation that we could use to describe various differential equations is a function or an equation that has x's, contains y, contains derivatives of y with respect to x, and could have various degrees of derivatives of y with respect to x. And this is just a fancy way of saying different combinations of independent, dependent variables and higher or different degrees of derivatives. So this is the differential equation, but the thing that makes it an initial value problem is if we have some condition. If we say that for a given x value, x sub 0, it pertains to a given y value. The phrase or the word initial in initial value comes from the concept of if you're looking at a scenario where you have a starting moment, a starting time, a starting weight. Initial just means where you started. So when we're solving this differential equation, we have the condition that when we find our explicit solution, we could call it f of x or y of x, when we have the initial x value that corresponds to a specific starting y value, whatever the initial x condition and whatever the corresponding initial y condition is. Then we may also have in our first derivative, we might also call that, for example, f prime, when we have our initial x value, there's a corresponding y that goes with that. Might see it written like this. In our first derivative, with a given initial x value, there's a corresponding y that goes with that. And we could have one of those, we could have two of those, we could have more. The number of initial conditions that we need is dependent on the degree of the differential equation, or the order of the differential equation. Is it first order, second order, third order? If you think about having a first order differential equation, we'll just do a simple example. And we might say, let's put a 2 here, that for that function, when x is 0, y needs to be 5. Remember that if we separate and integrate this, if we move the dx over and integrate both sides, y is x squared plus 3x plus a constant. Once we've integrated one time, there are no more differentials in there, so this is a general solution to our differential equation. It's explicit because it's solved for y, and if we only took one antiderivative, then we only get one arbitrary constant. So given this initial condition, we can find out what that arbitrary constant needs to be. So if we substitute a 0 in for x, y would be 5. So 0, 0. So we get that for this, under this initial condition, our c is going to be 5, which leads to the specific solution, y equals x squared plus 3x plus 5. When we don't have any initial values, we get a family of solutions. But when we have initial values, we get specific solutions. Think about if this was a second order differential equation, if this was a second derivative, then each time we integrated, we would get a different constant. So if we have two constants, we would have to have 2 points. So we would have 1 point for our function. We would have another point that corresponded to our first derivative. If it was a third degree, third order differential equation, then if you took 3 antiderivatives, you would get 3 constants. If you have 3 arbitrary constants, then you have to have 3 different points in order to find out what each of those constants need to be. Now I say integrate 3 times, and those are for specific types of separable differential equations. Generally speaking, that's not what we're going to do on most second order and third order differential equations, but on the types of differential equations we've done in the past, if we could isolate our differential and have just our variables on the other side, then that's how we got rid of the differentials. We integrated. But as we get farther along, there are going to be other techniques that we use. So let's work through an example. Let's suppose we have this solution c1 e to the negative x plus c2 e to the 2x. Let's show that it's a solution, and let's determine what C1 and C2 need to be if when x is 0, y is 2, and if in the derivative when x is 0, y is negative 3, for the differential equation d2y dx2, the first derivative minus 2 times y equals 0. So we're told that, hey, this is a solution to this differential equation. So how do we demonstrate that it is a solution? We take our 2 derivatives, we plug them in, and we show, yes, that will be true. And then we need to find specifically for these 2 points, what are our c values going to be. So our first derivative is to take the derivative of e to the negative x. Remember, it's the derivative of the exponent, which is negative 1 times c1, and then we keep our e to the power. For the next term, we have our c2. When we take the derivative of e to the 2x, we have e to the 2x times the derivative of the exponent. So we have those things and the derivative of the exponents. So that's the first derivative. We take the derivative of this again. We have this negative. We have e to the u. When we take the derivative of the exponent, we get another negative 1, which will make that a positive. For this term, we have this 2 times c2, and when we take the derivative of e to the 2x, we're going to get e to the 2x times the derivative of that, so another 2, which will give us 4c sub 2. So our first derivative and second derivative. So let's show that when we substitute these in, that this is a solution to the differential equation. So our second derivative minus our first derivative minus 2 times y. Y is our original function. Oops. And then all of this equals 0. So here we have a c e to the negative x. When we distribute that, that makes that another c e to the negative x. So that's 2 of those. and then that's going to make minus 2c e to the negative x. So these two positive ones and that negative one, those cancel. And here we have 4c sub 2 e to the 2x. This is going to make minus 2c sub 2 e to the 2x. That's going to make another minus c sub 2 e to the 2x. So that's minus 4. That's plus 4. So those cancel. So that leaves 0 on the left. So yes, when we take the second derivative of that, subtract the first derivative of that, minus twice that function, that does equal 0. So that is a general solution to our second order ordinary differential equation. Now the other question, the other thing it wanted us to do was find out, given the initial conditions on the right, what do C1 and C2 need to be? So when we substitute a 0 in, that needs to equal 2 to plug it directly into the function. So that e to the 0, that's 1, e to the 0, that's 1. So we get that C1 plus C2 equals 2. Then we have a value for our first derivative. Derivative was this, negative C1 e to the negative x plus 2 C2 e to the 2x. So when we substitute a z into that, a 0, we should get negative 3. So plugging 0 into the first derivative, we get an answer of negative 3. So that's 1. That's 1. So we get minus C1 plus 2C2 equals negative 1. If we solve that system of equations, add the two equations together, we get that 3 C2s equals 1. Divide both sides by 3, so C2 is 1/3. And then once we get C2, we can use either equation and solve for C1. And when we do that, we get that C1 is 8/3. Check see if I got. Oh, look, I copied something down. This was a negative 3 here. So that would make this a negative 1. So C2 is a negative 1/3. If that's a negative 1/3, this is not 8/3. This is actually, calculated that wrong to begin with anyway. That would be 7/3. So that's C1 and C2. So given initial values, we were able to find the specific solutions, not just any arbitrary constants, but the specific constants that work given our conditions. So we have 7/3 e to the negative x minus 1/3 e to the 2x. So that's working through an initial value problem. The other thing we want to look at is how we test for the existence and the uniqueness of solutions given a differential equation.